Greetings. This is Fundamentals of Surveying, and our topic for today is modern surveying. Introduction to modern surveying. Revolutionary changes have taken place in last few years in surveying instruments that are used for measuring level differences, distances, and angles. This has become possible because of the introduction of electronics in these measurements. With rapid advancements in the technology and availability of cheaper and innovative electronic components, these instruments have become affordable and easy to use. This presentation outlines developments in the technology for various survey measurements, such as digital levels, electronic distance measuring instruments, electronic theodolites, and total outlines.
Digital leveling systems for surveying rely on an electronic laser to scan a level staff with barcode markings. This type of level reduces the chance of human error when interpreting graduation marks, and a digital display ensures accurate readings. Operations of digital levels is based on the digital processing of video indications of a coded staff. At the beginning of measurement, a visual pointing of the instrument into the surface of leveling meter is performed. After that, the instrument automatically points the focus of its optical system on the surface of the meter, and then a rough correlation calculation is performed, followed by the precise correlation. An upside to digital levels is the potential for data integration. A surveyor can store readings in the internal memory and refer to them later, or transfer data to computers using external memory ports. Contractors should be aware that digital levels requires a battery which is often rechargeable to operate. Here are the types of digital levels used by the surveyors: Spinter 50, Spinter 150, Spinter 150M, Spinter 250M, Leica DNA 10 digital level, and Leica DNA 03 digital level. Advantages of digital level. First is correction of collimation error. Can be reliably determined and saved using the four integrated check and adjust procedures, or it can be entered manually. Minimize human error. Fatigue-free observation as visual staff reading by the observer is not required. User-friendly with easy-to-read digital display of results. Earth curvature correction. Measurement of consistent precision and reliability due to automation. Automatic data storage eliminates booking and associated errors. We can operate in low light conditions. Fast economic surveys resulting in saving time. And last is data on the storage medium of the level can be downloaded to a computer, enabling quick data reduction for various purposes. Components of digital level. The main components of digital level consist of two parts, the hardware and the software. First, both digital level and associated staff are manufactured so that they can be used for both conventional and digital operations. Second, typically digital level has the same optical and mechanical components as a normal automatic level. However, for the purpose of electronic staff reading, a beam splitter is incorporated which transfers the barcode image to a detector diode array. The light reflected from the white elements only of the barcode is divided into infrared and visible light components by the beam splitter. Fifth, the visible light passes onto the observer, the infrared to diode array. And last, the acquired barcode image is converted into the analogous video signal, which is then compared with the stored reference.
EDM instruments or electronic distance measurement instruments. There are three electronic distance measurement instruments. The first one is microwave instruments. It is also called tellurometers. These instruments use microwaves and they have been around since the 1950s. The second one is the infrared wave instruments. These instruments use prism reflectors that pick up amplitude modulated infrared waves at the end of the line. The last one is the visible light wave instruments. It uses modulated light waves to measure up to a specific range.
Next is electronic theodolite and total station. We will first tackle theodolite. Theodolite or transit is used to measure horizontal angles. This has evolved as follows: vernier theodolite, open-face and vernier-equipped instruments, optical theodolite, enclosed with optical readouts or micrometer-equipped readouts, electronic theodolites, enclosed with electronic readouts. Electronic theodolites operate like any optical theodolite, with one major difference that these instruments have only one motion, and hence only one horizontal clamp and slow motion screws. These are the characteristics of electronic theodolite. Digital readouts eliminate the personal error associated with reading and interpolation of scale and micrometer settings. Next is display window or unit for horizontal and vertical angles available at either one or both sides. Some digital theodolites have modular arrangement where they can be upgraded to be a total station or have an EDMI attached for distance measurements. Lastly, vertical circles can be set to 0 for horizon or zenith along with the status of battery shown in the display window. Next is total station. These instruments integrates the function of an electronic theodolite for measuring distances, digital data, and a data recorder. Angles and distances, coordinates, and height differences, and many other items can be computed, displayed, and stored into internal memory. Here are the features of total station. Total solution for surveying work. Most accurate and user-friendly. Gives off a point x, y, and z with respect to known point, base point. Compatibility with computers. Measures distance and angles and displays coordinates. Auto-level compensator is available. Can work in lesser visibility also. Can measure distances even without prismatic target for lesser distances. Waterproof. Onboard software are available. Can be used for curve layout after feeding data. New total stations have atmospheric correction and autofocus. In addition, this series incorporates a quick distance measuring mode and a high data storage capacity for increased productivity. The new total station gives the unique opportunity for long-range distance monitoring of up to 9,000 meters to a single prism. Using the scan functionality of software allows fully automated monitoring of the prism in direction of the line of sight. Basic principle of total stations. These instruments are measuring distances of prism poles mounted with prisms with the help of laser beam or infrared rays. These signals are emitted by the instrument EDM and reflected back to instruments by the prism mounted on the prism poles. The time interval between emission and reception helps to calculate the distance as the speed of these signals are precisely known. D equals T over 2 multiplied by V, where D is distance, T is total time taken, and V is velocity.
GPS. GPS stands for Global Positioning System. It uses signals in order to pinpoint a location on the Earth's surface. In addition to transmitting information about location, GPS can provide data about velocity and time synchronization for various forms of travel. GPS has 5 key uses. Number 1 is determining a position, which is the location. Number 2, moving from one place to another, or navigation. Monitoring the movement of a person or object, tracking. Creating a map of an area, mapping. And the last one is making precise time measurements, or in other words, timing. There are 3 methods of GPS measurement that are often used. The first one is the static GPS baseline. It is used to determine the coordinates for survey points by simultaneously recording GPS observations over both a known and unknown survey point for at least 20 minutes. Lastly, the data is processed in order to determine the coordinates within 5 mm accuracy. The second one is real-time kinematic observations. One receiver remains open over a base station while the other receiver moves between different positions, the rover station. Using a radio link, the position of the rover station can be calculated within a few seconds. As long as they are within 10 km of the base station, there will be a similar level of accuracy to baseline measurements that can be ensured. Number 3, the third one, is the continuously operating reference stations or CORS. In this operation system, a survey-grade GPS receiver is installed in a specific location as a starting point for any GPS measurements in the area. The GPS survey equipment can collect field data and combine it with course data in order to accurately calculate positions. GPS land surveying instruments. There are 6 GPS land surveying instruments. The first one is the GPS receiver. This instrument is used to receive signals from GPS satellites in order to make calculations. The next one is GPS rover rods. These instruments can be useful when it comes to extending the rover's reach. They can be made from a variety of durable materials and come in different lengths. The third one is GPS poles. It is used to mount GPS surveying equipment. These poles are durable and come in different lengths despite being a lightweight. GPS bipods or tripods. This is used for greater stability when it comes to mounting the GPS equipment, wherein they come in adjustable lengths and numerous sizes. The next one is GPS antennae. This equipment is used to be able for GPS systems to make signals from satellites. The last one is the total station. It is a combination of an electronic theodolite, electronic distance, and software running an external computer. It is used to calculate the coordinates of survey points using angles and distances.
Photogrammetry is the study of gathering information that are about the physical objects and its environment. This can be achieved in the process of recording, measuring, and interpreting with the use of images. Photogrammetry is also the use of surveying and mapping. It measures the distances between designated objects, which can be rendered into create 3D images. Photogrammetry has 2 types, which are aerial and terrestrial. Aerial digital is often used in topographical mapping, which starts with digital photographs. Close range or terrestrial type of photogrammetry are often used with a tripod or handheld cameras. They can be used in 3D models but not in topographical mapping. Capturing an image with the process of photogrammetry does not require any limit as long as it can capture the location. It is also required to change positions after taking an image of the previous one. Highest resolution is also a must when taking images with this procedure, and one of the most important part is not changing the viewpoint of more than 30 degrees.
Remote sensing. Remote sensing is the science of collecting information from a distance about objects or regions, usually from satellites or aircraft. It collects data by detecting the energy that is being reflected from Earth. And orbits. There are 3 types of orbits. The first one is polar orbiting satellites in an orbital plane, which are inclined towards the equatorial plane at approximately 90 degrees. This inclination allows the whole Earth to be sensed by the satellite, giving information of areas that are hard to reach through the ground. The second one is the non-polar. Low Earth orbits are at an altitude of usually less than 2,000 km above the surface of the Earth. Such orbits do not have global coverage but cover only a partial latitude range. The last one is the geostationary satellites, which follow the rotation of the Earth and move at the same rotation rate. Thus, the geostationary satellites appear to be fixed in one position. Reflected sunlight is the most common source of radiation detected by passive sensors, while active sensors use internal stimuli to collect data about Earth. Resolution plays a part on how sensor data can be used. Radiometric resolution is the amount of information in each pixel. Spatial resolution is described by the size of each pixel in a digital image and the area represented by that pixel in the surface of the Earth. Spectral resolution is a sensor's ability to distinguish finer wavelengths to have more and narrower bands. Temporal resolution is the time needed for a satellite to complete an orbit and retake the same field of observation. It also offers a global perspective and a collection of data on Earth systems. It has wide range of uses in variety of fields. Natural resource management. It is the data that can be used to mitigate harm to the ecosystem caused by an urban development and to determine the best way to protect the natural resources. Hazard assessment. The data that can be used to determine the effects of a natural disaster and to develop preparedness plans to be used before and during a hazardous incident. Ocean applications. It is the data that may be used in order to do better understand and handle the oceans. Coastal applications. The data that may be used for preventing erosion and coastal mapping.
Geographical Information System. Geographical Information System, or GIS, allows the analysis of data from various sources and formats. The data is visualized as layers, shape, features, and matches with attributes listed in a table. The data sets include elevation, road network, and boundaries, etc. Provides analysis of geometric or geographic information that solves complex problems regarding planning and management of resources. It is a system that uses hardware and software and methods and processes in the analysis of datasets. GIS emerged as a tool in land use planning and decision making. Components of GIS. Number 1, people. Involved in various tasks like data input, management of database, analysis, and system administration. Number 2 is data. Refers to spatially referenced data set consisting of geometric data and attribute data. Number 3, hardware. Refers to computer component on which the system operates. Number 4, software. Refers to different computer programs that provides the functions needed to store, analyze, and display geographic information. Example of GIS software are ArcGIS or ARCGIS, QGIS, and TERRSET, etc. Processes and methods. Refers to the management frameworks that are followed in the operation of GIS.